Okay, guys, so I added this up and I get g squared over 2, 945 over alpha to the 5. And that means, in fact, we've reproduced the order g squared contribution to the phi squared correlator. So this is great. So this was a very good example of using Feynman diagrams to calculate a correlation function, the two-point correlator in this case. And what you can see is the diagrams give us precisely the correct answer. Now, using Feynman diagrams really is just a case of practicing a little bit. So practice as much as you can. I would like to do a few more examples just to make sure that we've got the hang of it. What should be absolutely clear to you now is that the Feynman rules are just a very useful notation. They simplify our computations a lot. Actually, in naught dimensions, it might seem to you that things would have been easier to do it without the Feynman diagrams. And you're right, it would have been easier to do it in naught dimensions without the Feynman diagrams. But what we will find is in higher dimensions, it is much, much easier to use the Feynman rules to get the answer. And what's nice about working in naught dimensions is that you really get to understand all of these combinatoric pieces of the rule. So the 4 factorial for each vertex, the 1 over 2 for the closed lines, and the 1 over q factorials for equivalent lines, equivalent diagrams, and equivalent vertices. That's actually the tricky part of using the rules, believe it or not, and you can master that piece of using the rules in naught dimensions. So that's why what we've been doing is a useful exercise. Okay, so now the next thing that I would like to do is to discuss another correlator. And the correlator that I want to study is just the expectation value of 1. What is this given by? Well, this is given by evaluating z at j is equal to 0. And what is this equal to? Well, we've already gotten the rule for z. So this is a sum from n is equal to 0 to infinity minus g to the n over n factorial. Then we have d4 dj4 raised to the power of n, and we have e to the j squared over 2 alpha, and then we should evaluate this at j is equal to 0. And by now, I am assuming that you have memorized the formula for how to take these derivatives of the exponential. So I'm just going to write down the answer. It's 1 minus g times 3 semifactorial over alpha squared plus g squared over 2 factorial times 7 semifactorial over alpha to the 4. And then the next term would be minus, and it would be an order g cubed term. So you could very easily go ahead and calculate things to higher orders in g and check how good you are with Feynman diagrams. And I'd encourage you to do that a bit, okay? So this becomes 1 minus 3 semifactorial is just 3g over alpha squared plus, and then what is 7 semifactorial? Well, that's 7 times 5, which is 35, times 3, which is 105 over 2 g squared over alpha to the 4 plus order g cubed. So this is what we want to reproduce. So now when we draw our Feynman diagrams, well, we've got no dots because we've got phi to the power of naught. 1 is just phi to the naught. So that means there are no dots. So if we look at the order G contribution, for the order G contribution, there is just a single vertex. So that's what we've got. And then we must join the lines in all possible ways. Well, as we've said, there's only one way to do it, because all possible diagrams that you could draw are all equivalent. Okay, so now let's translate this into an expression. Well, you can see immediately there are 2 lines in this diagram. So we'll get 1 over alpha squared. There's a single vertex. So we've got minus g times 4 factorial, which is 24. And now let's put in the factors. So how many closed lines are there? Well, here's a closed line, that line in red, and here's a closed line, that line in blue. Both the red line and the blue line start and end at the same point. So we're going to have a 1, we're going to have a 1/2 squared, and this is for the closed lines. And then what about equivalent lines? Well, this red line is equivalent to the blue line. Both the red line and the blue line have the same start and end points. So we will have an equivalent line, which is just 1/2. So that's for equivalent lines. And if we work out what this is equal to, this is just minus g over alpha squared, then 24 over 2 times 2 is 4 times 2 is 8, so 24 over 8, which is 3. And this is the only diagram that we can draw with a single vertex and no dots. And what you can see is this exactly reproduces the order G term that we found above. So let's maybe just make it clear. What is the result that we're trying to reproduce? It is this red box. And indeed, we've reproduced the order G term. Okay, good. So now let's look at order G squared. So if we study order G squared, we need to draw all Feynman diagrams with 2 vertices, okay? So let's try to write down all of the diagrams that can be drawn with 2 vertices. If I remember correctly, there's 3 of them. So here is the first one, where we repeat this diagram that we had at order G. And then what we could do is we could connect 2 legs on each vertex. So we connect 2 legs on the first vertex to 2 legs on the second vertex, and we then close the remaining legs on the 2 vertices. And finally, we can connect all 4 legs between the 2 vertices. And that's it. That's the only thing we can do. We can have no legs joining the 2 vertices, 2 legs joining the 2 vertices, or all 4 legs joining the 2 vertices. There's nothing else. So convince yourself of that. Let's write down the value for each of these diagrams. Well, for this first case, this diagram, what is this equal to? Well, you can see there's a total of 4 lines. So we've got 1 over alpha to the 4. There's 2 vertices. So we'll have a minus g squared and a 4 factorial, which is 24 squared. Then how many closed lines do we have? Well, I think you can see that there is 4 closed lines. So we'll have 1/2 to the 4. This is for the closed lines. And I think by now you can really decide, check that for yourself. And then we've got 1/2 squared for the equivalent lines. Okay. And let's just make this clear. So this blue line over there is equivalent to that blue line over there. And this red line over here is equivalent to that red line over there. So we've got 2 pairs of 2 equivalent lines. So we've got 1/2 factorial squared. The blue lines and the red lines, of course, are not equivalent. Okay, so 2 pairs of 2 equivalent lines each. And then finally, do we have equivalent diagrams? Yes, there's 2 equivalent diagrams. So we need a 1/2. And that 1/2 is for equivalent diagrams. Okay. And are they equivalent vertices? Well, each diagram only has a single vertex. And if 2 vertices are equivalent, they must sit in the same diagram. So let's work out what this gives us. So we'll get a g squared over alpha to the 4. And then take a look at this. These first 2 factors give us a 1/2 to the 6 or a 1/8 squared. Okay. The reason why that 1/8 squared is interesting is that 24 divided by 8 is 3. So we will have a 3 times 3, which is 9. and there's still 1 over 2 left over. So we get g squared over alpha to the 4 times by 9 over 2. So you can check that those numbers, after you've multiplied them out, you get 9 over 2. Good. Now let's move on to the next diagram. So here it is. So again, count how many lines are there. I think that you'll have no problem in seeing that there's a total of 4 lines. There's 2 vertices. So we've got minus g squared and a 24 squared. Then how many closed lines do we have? Well, there's 2 closed lines. So we'll get 1 over 2 squared. And this is for the closed lines. Closed lines. How many equivalent lines do we have? Well, 2, so we'll get a 1 over 2. Just, okay, I'm sure you know this, but that blue line over there is equivalent to this blue line over there. They both have the same start and end points. So this is for equivalent lines. So equivalent lines. And then finally, so are there any equivalent diagrams? Well, there is only one diagram. But for equivalent vertices, yes, there are 2 vertices that are equivalent. This vertex over here is equivalent to that vertex over there. They both have 2 of their legs closed to produce a closed loop. And then the lines which run between the 2 vertices, their start and end points are unchanged if we swap the 2 vertices. So there are 2 equivalent vertices. So this factor here is for equivalent vertices. So what do we get if we multiply this out? Well, we've got a g squared over alpha to the 4. And then we've got 24 over 4 times 24 over 4. But 24 over 4 is 6, so it's 6 times 6, which is just 36. Good. Okay, let's now take care of the final diagram. And the final diagram looks like this. Good. So what is this equal to? Well, once again, there are 4 lines, so 1 over alpha to the 4. There's 2 vertices, so we've got a minus g squared and a 24 squared. Then we've got a 1 over 4 factorial because all 4 lines are equivalent. Okay, all 4 lines in this diagram start and end at the same point. And then we've got a factor of 1 over 2 for equivalent vertices. If we swap the 2 vertices in this diagram, we don't change where lines begin or end. Good. So what is this diagram equal to? Well, again, we'll have a g squared over alpha to the 4. And then we've got 24 squared over 4 factorial, which is the 24, and 24 divided by 2 is just 12. Good. So we've worked out what these 3 diagrams are. Now let's just add them up. So we've got g squared over alpha to the 4 times by 9 over 2 plus. Now, let me put everything over 2. So for the second term, which is g squared over alpha to the 4 times by 36, I'm going to write this as 72 over 2 plus, and the last term is g squared over alpha to the 4, and instead of writing 12, I'll write this as 24 over 2. Now, 24 plus 72 is 96. 96 plus 9 is 105. So we'll have 105 over 2 times by g squared over alpha to the 4. And this is what the sum is equal to. And if you take a look, this is exactly the order g squared term in the expectation value of 1. So we've reproduced this red box here by summing the Feynman diagrams as shown below. Okay, we'll continue in a moment.